Hello everyone. We're going to continue our discussion on vectors. This is vectors part 4. So let's get started. Properties of the matrix vector product. So in the previous session, we already discussed how we can represent a vector in the form of matrix. And in this session, we're going to dive a little more in detail what happens when you multiply a matrix, which is holding scalar values, with a vector represented in the form of matrix, and when we are performing algebraic operations on them. Alright, so the first operation is distribution of addition across matrix over the vector is actually distributed in nature. That means if you have a matrix A here and you have two vectors u and v here, so when you add the two vectors together and multiply it with the matrix equals, if you multiply the vector with the matrix and then you multiply the second vector with the matrix and then add the two together, so the addition is distributed. The second property is if you have a scalar c and you have a vector u, so if you multiply the scalar with the vector and then if you multiply it with the matrix will be equal to if you multiply the matrix with the vector and then you multiply it with the scalar values. So this property also holds good if you have a matrix vector relationship. Okay. So a quick recap from the previous session. Again, we've already seen we can intertwine matrix equations and represent them as vector equations, and vector equations can be represented in the form of matrix equations. We'll just do a quick recap here. So let's say we have quite a few number of vectors v1, v2 until vn in some Rm dimensional space, and this is our vector equation x1 v1 plus x2 v2 plus until xn vn, which equals to some consistent value. So then this matrix equation Ax equals B we can represent in the form of matrix, and we know how. A equals v1, v2, v3, where v1 is an entry across the first column, v2 is an entry across the second column, and so on and so forth until all the columns are satisfied, that is until n in this case. And x equals all these coefficient values of x1, x2 until xn. So this is the representation. The second one being, so we have A as a matrix which is an m cross n matrix. That means it has m number of rows and n number of columns, and Ax equals B is the equivalent vector equation. So if I have to convert it other way around, then this becomes x1 v1 plus x2 v2 until xn vn, and this equals B. So here v1, v2 until vn are the vectors and x1, x2 are the entries of x values. So we've seen how we can interchange the two representations. In the previous slide we saw that we had this equation and we were able to write it down in the form of Ax equals B, and then in this slide we see that the equation given to us is in the form of Ax equals B, and we can actually devise it in this equation. Alright. Matrix equation, vector equation, it's continued. We have a quick example here. So write the vector equation as a matrix equation where v1, v2, v3 are the vectors in R cube. So if you see closely, this is actually x1 v1 plus x2 v2. In the previous slide we discussed this to be an equation, right? Plus minus of x3 v3, correct? So this is what we have as an equation. Now we need to represent this in the form of Ax equals B. We already saw that A is actually a matrix with holding all the vector values, correct? So v1, v2, v3 are the vectors here, and x entries are 2, 3 and minus 4. So the representation in this case becomes Ax equals v1, v2, v3 spanning across the columns, which we already saw the previous slide, and then 2, 3, 4 becomes the x entries, and this equals 7, 2 and 1. So this is how you convert an equation which is a linear equation in the form of matrix representation. So now we have multiple ways of writing system of linear equations. We discussed 3 of them in the previous session. We will append just one more for this session. So we've seen that linear system of equations can be represented in the form of augmented matrix. We just discussed it in the previous session, and a detailed video is also put on under matrices for this. I'll link them in the description box again. The second representation is in the form of vector equation, where you take off the coefficient x values outside and then put the vectors together. And then we've also seen the third representation, which is in the form of matrix equation just now. 2, 1, 3, minus 1, minus 2. You're taking out all the coefficients and then you're taking the variables outside and equating it with the value. So now there's another way for computing AX because of the fourth representation that we have added, and this is as under. So let's say we have A1, A2, AN to be some form of a matrix, and we have x1, x2, xn as the entries. So we've already seen this equation, how we represent them. Now if we were supposed to multiply the vectors with the matrix, this is how we do. So we have 1, 3, 1, 2, 4, 2, and we have x entries here 1, 2, 3. So what we can do, we can simply take the first row and then just multiply it with the entire column, as you can see here, and then we can take the second row and then multiply it with the entire column, as you can see here. So we have 1 multiplied by 1 plus 3 multiplied by 2 plus 1 multiplied by 3, and then we have 2 multiplied by 1 plus 4 multiplied by 2 plus 2 multiplied by 3, and then we get the values. So this is another way for computing AX. So this was sort of, this session was sort of a revision to what we've been discussing, and just a few more concepts. That is, I've just added one more representation of representing linear systems of equations. And we've seen how matrix and vectors, when multiplied together, gives us like what is the output in that case, and we've also seen some important properties in this case. So that's pretty much it for vectors part 4, and we will be continuing our discussion in the next session. Yep. And again, if you have any queries or if you have any questions, just feel free to drop in the comments or get in touch to me through the website. And yep, that's pretty much it. Thank you so much.